We continue in this lecture with the differential entropy. In the previous lecture, we have seen that Gaussian distribution or multivariate Gaussian distribution maximizes the entropy of any random variable with the same covariance matrix. We have given the results for real random vectors. So if you have complex random vector, then the result is very important and pertinent for our case. So we extend the result what we have achieved before to that of the complex random vectors. At this point, I'd like to remind you or tell you that these results are very fundamental, and you can find the reference in a paper by Nasir and Massey of 1993, where they have shown that the zero mean circular symmetric complex Gaussian random vector maximizes the entropy. So we will be just showing you the result, which is almost straightforward given whatever we have described, although the derivation of this result is not so straightforward. But for our case, since we are interested in the results mainly, with whatever build up we have achieved in the previous lecture, in this one we are going to extend that and show the result for the complex Gaussian case. So in the case of complex Gaussian, the f of x is given by 1 upon pi raised to the power of n times determinant of k e to the power of minus x minus mu Hermitian times k inverse times x minus mu, and remember all of these are vectors. This is a matrix. So this is the expression of fx. So if we have to calculate h of f, what we'd be getting is and what is important, h of f would be getting as log 2 of pi e raised to the power of n times determinant of k in bits, or if we have ln pi e to the power of n pi k in nats, right. So this is the expression of h of f when x is complex Gaussian distributed with n components. And again, if we try to see if g is random, if g is the distribution of a set of random variables like g of x, like we have done over here, like we have done in the previous lecture. In this case, again we could show that h of g is upper bounded by h of f, which is given by this expression. So basically this is the maximum entropy provided x is zero mean circular symmetric complex Gaussian, and we have explained this definition, and also there is some further definition that g is proper. So if we do this, g turns out to be proper, and this would be a very important expression in our results on capacity. So with this we move on further, and we'd like to give you a explanation or an intuitive feeling of how do we get the expression of capacity. So we are not going to derive the exact expression of capacity, because that's not our end goal. Because we'll be using the expression, it's important that we have an intuitive understanding of what we are talking about. So for this we'll be using again all the things that we have established, and what we need at this point is asymptotic equipartition of energy, or asymptotic equipartition property, not asymptotic equipartition of energy as you learn in typical physics. So basically we'll be talking about AEP, and AEP states that if x1, x2, so on are independent identically distributed following distribution of p of x, then minus 1 upon n log p x1 x2 up to xn tends to hx in probability if n is large, right. So this statement is very indicative. I mean, this gives us very important results, and it's quite nice to understand what it tells us. So if we take a look at this expression on the left hand side that we have here, it is 1 minus 1 upon n log of p x1 x2 up to xn. So this we could also write as minus 1 upon n log px1 plus log px2 and so on plus log pxn, which is basically minus n sum of I equals 1 to n log pxi, right. So if we take a look at this, it's almost the sample mean of this particular thing. So this we could write it as almost expectation of log px, right. This is what we could write, because this, if n is very, very large, then by weak law of large numbers, when n is very, very large, we have very large value of n, by weak law of large numbers we could write this as the expectation of these variables. And this would be also, so there is a minus expectation, I am very sorry for this, there is a minus sign, minus expectation. So minus expectation of log p of x, if we would remember, then we could write this as h of x, because h of x was defined as sum over I equals 1 to n px log px with a minus sign. So this was basically the leading to the expectation operation, but when n is very, very large, by weak law of large numbers, we said we could write this as expectation, and from this this we had written it as minus expectation of log p of x. So this was defined as h of x. In the integral form, instead of the summation, there was the integral sign. So basically now we are using this definition and saying that this could be written in probability sense as h of x. Now what are the things that this leads to? So if we move down further, again starting from this point, what we have is minus 1 upon n log of 2 px1 x2 xn is equal to h of x. So clearly we have minus n, we have n hx, we have a minus, so basically log 2 px1 to xn is basically this, right. So we could write p of x1 x2 up to xn is equal to 2 to the power of minus hx minus nhx. So what is this p x1 x2 xn being equal to 2 to the power of minus nhx? So if we look at this expression in details, we get some intuitive understanding of what is the meaning of this. So x1 x2 up to xn is basically a sequence of observations that we get. So it's a sequence of random variables, right. And we have said earlier that it's an IID. We have said here it's an IID with individual distribution p of x. So x1 to xn is basically a sequence, and p of x1 x2 xn is the probability of this particular sequence to occur. And without choosing a particular sequence, we said that this appears to be 2 to the power of minus nhx. So this in turn means that if I take a random sequence x1 to xn, when n is very large, the probability of that sequence is 2 to the power of nhx. And as I take as many sequences, all of those sequences have these probabilities. So for instance, I could take 0 1 0 0 up to a certain number. I could take 0 0 1 0 and so on and so forth up to a certain number xn. The probability of an arbitrary sequence is 2 to the power of nhx. This is somewhat difficult to get initially, but if we look at what we are doing here is I am drawing an outcome. I am drawing a particular sequence x1 followed by x2, x3 and x4, and I say that probability of x1 is the same as that of probability of x2 and so on and so forth. They are all independent and they are all identically distributed. So if we take let us say zeros and ones coming out, and then we say the probability of 1 is equal to, let us say, some p1, and probability of a 0 is, let us say, a p0, or which is equal to 1 minus p1, and we have such sequence. What we are going to get is the number of ones in such sequence is basically n times p1 when n is very, very large. Number of zeros in such sequence is basically again n into p0. So if I ask what is the probability of this particular sequence, it's basically the probability of 1 raised to the power of p1 times probability of 0 raised to the power of np0, because all of them are IID, right. So So this is basically the probability of that particular sequence, and all we are saying is that that value is equal to 2 to the power of minus nhx, and there could be many such sequences that comes up. I mean, it's not all of the sequences, but what it's essentially saying, that if I pick an output, if I take an x1 from that from the source, and what's the probability of that being 1? It's basically p1. If I take another outcome, what's the probability of that being 1? Is basically p1. So if I keep doing this experiment for a very long time and generate a very long sequence, on an average I'm going to get n times p1 number of 1s and n times p0 number of 0s. So just try to imagine that you're doing this experiment over and over again for very large sequence xn. It would turn out that each one of them would have the probability 2 to the power of minus nhx. This is in probability. So that means there could be other sequences. There could be sequences which are like all 1s. There could be sequences, right, all 0s. But if n is very large, we could generally say that just a typical sequence, if I take out a sequence from that, a typical sequence would have n times p1 number of 1s and n times p0 number of zeros in that. So the overall probability of the sequence is p1 to the power of n p1 and p0 to the power of n p0. If you would take the now if I say that what is hx, if I say what is hx, hx is basically minus p1, that is probability of getting 1 times log of probability of getting 1 minus p0 times log of probability of getting a 0, right, p0. And if there are n such symbols, I would say we have n hx is equal to minus n p1 log of p1 minus n p0 log of p0, and basically if you take a look at this, it's basically log of minus log p1 to the power of n p1 times p0 to the power of n p0, and again this particular sequence p1 n p1 p0 to the power of n p0 is equal to 2 to the power of minus nhx. So I've started with hx. If I take n such sequences, n such symbols, what I get is n hx, n times hx, and the right hand side is straightforward. So what we get is the probability of that sequence is indeed 2 to the power of minus nhx. So one needs to spend a little bit of time in trying to capture what it is talking about. So we usually define a set known as the set of typical sequences. The set of typical sequences. All we say is that it contains sequences which occur with very high probability, and that probability is 2 to the power of minus nhx, and all the sequences in that set are equiprobable. So that means I am drawing a very large sequence, a very large sequence. We can clearly say that number of 1s in them is np1, number of zeros is np0, and there could be many such sequences, and each of those sequences occur with equal probability provided the occurrence of 1s and zeros are independent and they are identically distributed in any of the locations. So those sequences which are likely to occur, are highly likely to occur, are known as typical sequences, and the probability of those sequences are given by 2 to the power of minus nhx, and they are all equiprobable. So if we consider a big set of sequences, if we consider a big set of sequences, we will find that there is a subset of sequences. This is the full set. This is the set of typical sequences usually indicated in this manner, which has all these sequences. So, and if they are all equiprobable, all we can say is that the number of sequences in this set is basically 2 to the power of nearly equal to 2 to the power of nhx. So this is also an outcome of this particular thing. So number of sequences in that is basically 2 to the power of nhx in this typical sequence, or in other words, what is usually said is that the number of elements in n is less than or equal to 2 to the power of n h x plus epsilon, and number of sets in the typical sequence is greater than or equal to 1 minus epsilon 2 to the power of minus n h x minus epsilon for large n. So, basically this bounds. So, what we are trying to say is we are not going into the proof of this, although it is not very difficult to prove it, because again we are interested in the result. The number of such typical sequences is 2 to the power of n h x. So, we have it also can be shown that can be easily quickly told in terms of 2 to the power of minus n h x is the probability of a sequence. All the sequences are equiprobable. So, the number of sequence in that case is 2 to the power of n h x. You can also justify in that sense. Okay. So, once we have said this, we move on to try to understand that how do we take advantage of this particular thing. So, again detailed description of this can be found in any book on information theory. Now, suppose we have a typical communication channel, and there is a transmitter, there is a channel, there is a receiver. So, at the transmitter what we take is sequences, right. So, we take sequences. All we are saying now is the transmitter generates a sequence, and the sequence is a sequence of symbols, and if it is if the symbols are equiprobable, then we can form a typical sequence, and each such sequence occurs with a probability of 2 to the power of minus n h x, where n is the number of symbols in that sequence. And what we get over here is y's, y1, y2 up to yn, generated by x1 to xn, and the channel lies in between. So, if we take a very simple case where there is a 1 and a 0 that is being generated by the source, what the channel could do is 1 could remain a 1, 1 could become a 0 could remain a 0, or 0 could become a 1. So, this is one of the simplest channel that we can think of, where 1 becoming a 0 is identified the probability of error, and 1 minus p e is the probability of being correct. In a symmetric channel case, we are going to have this as p e and this as 1 minus p e as well. So, basically every symbol that goes out has a probability of becoming some symbol. So, basically if I take the example of a, b up to z, let us say I have these 26 characters. When I send a, there is a certain probability that a could remain a, there is a certain probability a could become a b, and so on, with a certain probability of a becoming a z. So, if I take any particular sequence from this, I take x1, x2 up to xn, I would find a corresponding sequence of it becoming certain y1, y2 up to yn, where y1, y2, yn can take values from this. So, now since we have talked about the typical sequence being generated at the source, we could also say that at the receiver, because of a particular sequence, there is a sequence that gets generated. Now, clearly because of 1, in this example 1 could become a 1 or 1 could become a 0, and in this example a when transmitted could become a, could become a b, or could become a z with certain probability. This particular sequence could produce many sequences, right, and the typical sequence has a probability of 2 to the power of minus of n h y conditioned on x, y given x. So, what it is trying to say is basically when a particular sequence is taken, and if I look at all these sequences that get generated because of this, a typical sequence will have a probability this, and the number of such sequences would be 2 to the power of minus n h 2 to the power of n h y given x. So, we can draw a broader picture and say that suppose I have a source which selects from certain points or certain sequences. Now, these points indicate sequences x1, x2 and so on. When it goes through the channel, it produces y1, consider this as a sequence, y2, y3 and so on. So, this x1 sequence, this is x1n indicating it is a particular sequence, produces a certain set of outputs. So, this generates a certain set of outputs, this generates a certain set of outputs, and the number of such sequences in this particular one is 2 to the power of n h y given x, that is what is being meant, and each outcome with a probability of 2 to the power of minus nh y given x. So, what is the number of typical sequences in y? If h of y indicates the entropy of this output, so basically n h y is the entropy of the output when n symbols are taken together. So, the typical sequence would have a probability of 2 to the power of minus n h y, and the number of such typical sequences would be 2 to the power of n h y. So, there are 2 to the power of n h y number of typical sequences. One particular sequence produces 2 to the power of n h y given x. So, what we are saying is, out of all these sequences, one sequence produces so many sequences, this particular sequence produces so many sequences. So, if we have to achieve low error probability, or if we have to say that when x1 sequence is transmitted, x1 n, or when x2 n sequence is transmitted, all of these sequences are received, right, with certain probability, all of them are received with equal probability, and these sequences are received with equal probability when x2 sequence is sent. The job of the receiver is to identify what sequence is being transmitted. So, if we have to ensure that when x1 is transmitted, the receiver does not decode it as x2, it decodes only as x1, then we have to ensure sufficient separation of these sequences. In other words, if this contains, let us say, 4 sequences, for example, this contains another 4 sequences, we have to ensure that when a particular sequence generates any of these 4 sequences, the receiver would say, okay, the particular sequence 1 was generated, whereas when these 4 sequences are generated, the receiver would say that x2 was generated. So, to ensure there is separation between these sequences. So, in total, if there are 2 to the power of n h y typical sequences, and if one particular sequence at the input produces 2 to the power of n h y given x number of such sequences, we can have 2 to the power of n h y upon 2 to the power of n h y given x number of different sequences. So, we could have so many such different sequences. In this, there would be so many such sequences. So, this number, this count 1, 2, 3, 4, this number would be given by this, right. So, this is equal to 2 to the power of n h y minus h of y given x, right. So, what we would like to do is to increase the transmission rate, that means send as many sequences as possible. So, we want to maximize the number of separable groups at the receiver, so that maximum number of symbols at the transmitter could be sent without confusing, without any ambiguity. So, basically we are trying to maximize this ratio. So, at the job would be to maximize this ratio. So, that maximization of that ratio would mean maximization of this term, which would mean maximization of this term. So, maximization of this term, now you could easily recognize this as I x y, and which is the mutual information, right. So, what we can get an indication from this particular explanation is that why do we have that channel capacity denoted as max of I x y over all possible distributions of the source symbols, either f x or p x in case of probability mass function. So, what we have indicated over here is that this is the definition of capacity that one would typically follow, and we have given an intuitive explanation of why such a description comes. So, using, if you look at this description, we have I x y, which we have defined for both discrete and random discrete and continuous variables. We have defined h y and h of y given x, and what we now need to do is to find the distribution of source symbols, or the distribution of the source for which this expression is maximized. Again, just giving you hints, we have seen that the distribution which maximizes this capacity expression, or this mutual information, which is determined by h y, is again we have derived for continuous random variables, it is the Gaussian distribution. So, in the we will continue this particular lecture, and in the next one we will see that the Gaussian distribution maximizes the mutual information between the source and the distribution for a Gaussian channel, and that will again finally lead to the expression of capacity. Thank you.